Okay, so welcome to Unit 5. Unit 5, we're going to be talking about a sampling distribution. All right, so I sort of have that sampling distribution highlighted. We're going to go over in just a couple of minutes what exactly that means. This section is vital basically to what we're doing for the rest of the year, so it's really important that you understand the concept behind a sampling distribution. So please make sure that you take the time to do the practice problem. All right, so what exactly is a sampling distribution? So after we go over this section, you'll be able to understand the difference between a parameter and statistic. Hopefully, you remember that from the previous sections. You're going to use a sampling distribution of the statistic to evaluate the claim about a parameter. So that vocabulary, statistic, and parameter is going to come into play. Distinguish between, this is going to be tricky, the distribution of a population, the distribution of a sample, and a sampling distribution of a statistic. So it seems like a lot of vocabulary, but hopefully by the end of the section, you'll really understand the difference between the three. And then determine whether or not statistic is an unbiased estimator of a population parameter. So remember that biased means we're either going to over or underestimate consistently the true population, mean, proportion, etc. You're going to then be able to describe the relationship between a sample size and the variability of a statistic. So remember, variability means is there a wide range of values, that's a high variability, or a low range of values, that's a low variability. All right, so what exactly is a sampling distribution? There is a huge key difference between a sampling distribution and the distribution of a sample. So please make sure that you have watched the YouTube video from the AP Stats Guy on sampling distribution. If you watch that 10 to 12 minute video, you will understand completely what a sampling distribution is, and this section will be very easy to go through. He makes the concept very clear and very easy to understand. It will be helpful to watch before you review this PowerPoint. So as you're going through this, if you watch this, it's going to be very easy. So the video is posted under 5.1 content. It's the first video. The link is also posted below, so you can copy and paste this into your browser and watch it. Please watch it. It will make everything very clear. I guarantee you, you will have a aha moment on what exactly a sampling distribution is. It's also a funny video to watch. All right, so first, let's just take a quick introduction to what we're talking about before we go into what exactly a sampling distribution is. So remember, the process of statistical inference involves using information from a sample to make conclusions about a population. All right, so we're most likely never going to get the population mean height of everybody in the United States. So we take a sample to make a conclusion about the population. Okay, so when we take different samples are going to yield different statistics. So let's say I take sample 1 of heights in the United States. That's going to give me one average. Then I take a second sample. Since that can be different people, that's going to be a different average. Then I take another heights of people in the United States. That's going to end up being a different sample, even if they're random. So the heights are all going to be just a little bit different. So we need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. So we'll go over in a second what exactly a sampling distribution is, but we have to be able to understand what that distribution looks like in order to make conclusions about the population. So think of a statistic as a random variable because it takes numerical values that describe the outcome of the random sampling process. All right, so what does that really mean? All right, so let's say we have our population. Okay, and then within that population, we take a sample. From that sample, we collect data from a representative sample and we make inference about the population. With a sampling distribution, we take many samples. So we've taken a sample, get the mean. Take another sample, get the mean. Take another sample, get the mean. And from all of those samples that we've taken, we can then make an inference about the population. So as we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. So please be careful with your symbols here. It is very important that you understand the difference between a parameter and a statistic and the symbols involved in those two. If you use the incorrect symbols, you will be marked incorrect. Okay, so please keep that in mind. So just as a quick refresher, a parameter is a number that describes the character. All right, so just a quick refresher of what the symbols will look like for means and proportions, because throughout the rest of the year, that's what we're going to be dealing with. All right, we're going to be dealing with means and proportions. So with means, our parameter or population symbols are mu, so that's the mean of the population, and sigma, that is the standard deviation of the population. Okay, so this is all your population. So when you use these symbols, you have to understand that you're talking about a population. X bar is the mean of the sample, and S of X is the standard deviation of the sample. So when you use those two, understand that you're talking about the sample. So for proportions, P is your population proportion. Sigma with a little p underneath it is your standard deviation of your population. P hat is the proportion from a sample, and sigma with a p hat is the standard deviation of the sample. Okay, so I know that's a little bit tricky. If you're ever not sure, just keep in mind, so proportions, anytime you're dealing with proportions, just make sure you either put the p or the p hat next to the standard deviation so we know if you're talking about the sample or the population. Please make sure that you understand the distinction between statistics and parameters. If you use the incorrect symbols, you will lose points. So just as important as it is to understand, it's important to understand how to use the symbols when you are completing your problems. So when you're making conclusions, which we'll get to later on, okay, please make sure that you use the language such as the true mean or the population mean. So remember that we're using the samples to estimate the true mean or the population mean. If you just use the word mean, we're not going to know what you're talking about. Are you talking about the sample? Are you talking about the population? Be very specific in describing what you are discussing. Okay, so let's just take a look at some of that vocabulary for a minute. Let's suppose that I select 100 seniors from Fairfax County and record everyone's GPA. Now, important here is the fact that I randomly selected 100 seniors. So if you remember, in order to do inference, in order to make a conclusion about the population, we have to have random selection. So random selection allows us to do inference. Without random selection, we can't necessarily make inference about the larger population. Okay, so here's 100 seniors GPAs. So let's just take a minute and talk about the statistics and parameters involved in this data. All right, number one. So the 100 seniors make up one possible sample. Specifically, it was a simple random sample. All seniors in Fairfax County make up the entire population. So remember, the population isn't the population of the United States. We're defining what the population could be. So in this specific case, we define the population to be all seniors in Fairfax County. What will our correct symbols look like for the statistics or the sample of my 100 seniors versus the parameter or the population of all seniors in Fairfax County? Okay, the sample mean, or X bar, is 2.5470. So that's saying the sample mean of my 100 seniors, their mean average GPA is 2.54. The sample standard deviation, so the standard deviation of my 100 seniors, is 0.7150. The population mean, mu of x, and the population standard deviation are unknown. We didn't collect every senior in Fairfax County, so we don't know the population mean and standard deviation. What we're going to do in this section is we're going to use x bar, the sample mean, to estimate the population mean, and the sample standard deviation to estimate the population standard deviations. And we're going to decide, whether or not the estimates are reliable. All right, so we've already discussed that a number that describes a population is called a parameter. So the mean and mu and sigma are both parameters. A parameter, so that was dealing with means, so let's just take a minute and talk about proportions. So a parameter for proportions is just represented by the letter P. So if you write P, we're assuming that it's the population proportion. A number that is computed from a sample is called a statistic. So remember that x bar and S of x, which is your sample standard deviation, are both statistics, not parameters. Parameters your population. A statistic for proportion is represented by p hat. So that hat's really important. That tells us that we looked at a sample and not the entire population. So if I had chosen 100 different seniors, then I would have a different sample, but it would still represent the same population. All right, so even though I had chosen 100 different seniors because it's random, all right, I could get 100 different seniors, but it's still a representative sample of all of the seniors in Fairfax County. Now, here's what we're going to be taking a look at in this section. If I had chosen 100 different seniors, then it's probably going to produce a different statistic. So my sample mean and sample standard deviation of the average GPA is going to be a little bit different. So what does that mean when I get different samples and different statistics? Okay, so before we take a minute and look at what it means whenever I collect different samples of size 100, let's just make sure that we understand the difference between a statistic versus a parameter. All right, so in each of the settings, please just take a minute, identify the parameter, the sample, and the statistics in each of the following settings. Please try and use the correct symbols. The more practice that you get with them, the easier and more natural it will be as you're completing your problems. So a pediatrician wants to know the 75th percentile for a distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates the 75th percentile in the sample of 56 inches. A Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So just go ahead, take a minute, pause it. In each case, identify the population, the parameter, the sample, and the statistic. Okay, so let's just take a look at the answers. So in our first question, our pediatrician, the population is all 10-year-old boys. The parameter of interest, so this is the population that we're looking at, is the 75th percentile for all 10-year-old boys. What was our sample? Our sample was our 50 10-year-old boys included in the sample. The statistic is 56 inches. The 75th percentile of the heights in the sample. So if you wanted to write X bar, you could. Okay, so how about letter B? So letter B, the population is all 12 to 17-year-olds in the United States. The parameter P is the proportion of all 12 to 17-year-olds with cell phones. The sample is the 1,102 12 to 17-year-olds. And the statistic is the sample proportion. Notice we have p hat, which is 0.71. All right, so let's just take a minute and talk about sampling variability. Now, sampling variability, so the reason I have the sampling highlighted, sampling is the reason that's highlighted is because I'm not just going to take a look at that specific 100 seniors from Fairfax County. I'm going to find 100 seniors from Fairfax County and find what their average GPA is. And then I'm going to take another 100 seniors from Fairfax County and find what their GPA is. And then I'm going to take another 100 seniors from Fairfax County and find what their average GPA is. That's the sampling. Okay, I'm taking multiple samples, and from those multiple samples, I am finding the mean from the multiple samples. Okay, so from that sampling, what we're going to ask is we're going to say, how can X bar, or how can our sample mean, be an accurate estimate of our population mean? After all, different random samples would produce different values of X bar. So if I took a sample of 100 seniors, their mean might be 2.5, and then I take another 100, their mean might be 3, and I take another 100, theirs might be 2.6, okay? How can I give a good estimate if they're all going to be different? The basic fact is called sampling variability. So what does that mean? That means the value of the statistic varies in repeated random sampling. So all those means that I find of the GPAs, if I take 15 different samples of 100, the statistic is most likely going to be different or vary from sample to sample. Okay, so to make sense of sampling variability, we have to ask, what would happen if I took many samples? All right, so in my population, I took a sample of 100 seniors, 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 okay, and I look at all of those average GPAs, okay, what does that tell us about the population? Okay, now each of these were averages. Wouldn't it make sense then if I took the average GPA, 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 average? What would happen if I took the averages of all of those GPAs? Wouldn't that be a better estimate of my population rather than just one sample? Okay, so let's just take a look at what the sampling variety looks like. So let's let P hat represent the proportion of seniors in a sample of 100 seniors whose GPA is 2.0 or higher. Okay, so I took these each represent a sample of 100 seniors. So P hat 1 is going to say, okay, I had 100 seniors and 78% of those had a GPA of 2.0 or higher. In sample 2, 72% of them had a GPA of 2.0 or higher. Sample 3 had a GPA, 81% had a GPA of 2.0 or higher. Okay, so hopefully you're getting the picture there. So all of the P hats are the proportion of seniors in the sample of 100 whose GPA was 2.0 or higher. So we are taking a look at a whole bunch of different proportions. In this case, we have 10 of them. If I compare the many different samples and the statistic, in this case, P hat is very similar, the sampling variability is low. So take a look. We have 0.78, 0.72, 0.81, 0.7, 0.68. Okay. You would have to make the decision, is the sampling variability low? Are they all about the same? Okay, or is it high? How will I know if it's high? So if I take many different samples and the statistic is very different, then the sampling variability is high. All right, so and it's sampling because I have multiple samples from the same population. Okay, so how can I create a sampling model of all of these proportions? The sampling model of a statistic is a model of the values of the statistic from all possible samples of the same size from the same population. The sampling model is putting all those P hats in a distribution or a curve. So basically, what I did is I have 10 different samples, okay? The sampling model would be if I were to take all of these samples and put them on a number line and take a look at the distribution. Okay, so then I could draw a curve, hopefully draw an approximately normal curve, and see where all of these lie. Okay, so the sampling model is taking all of these proportions and putting them on a normal curve. Okay, so if we took every one of the possible samples of size n from a population, so if I took every possible sample of 100 students from all of the seniors in Fairfax County and found all of their P hats of proportions greater than 2.0 and put them in a distribution, that would be the sampling distribution. Okay, now it's important to not confuse this with the distribution of a sample. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, so let's just make that a little bit easier. So what am I talking about with a sampling distribution and telling you don't confuse the distribution of a sample with the sampling distribution? Well, that already sounds confusing. So let's take a minute and make that a little bit more clear. Okay. So in practice, it is difficult to take all possible samples of size n, which will give us the actual sampling distribution. Instead, we can use simulation to imitate the process of taking many samples. So one of the uses of probability theory is to obtain sampling distributions without simulation. So we're going to get a sampling distribution to represent the population distribution. But let's just take a minute and understand the difference between distribution of a sample and sampling distribution. Okay, so let's just take a look at the sampling distribution of our proportion of 100 seniors that have a GPA of 2.0 or greater. All right, so let's take a look at the sampling model. Okay, the sampling model, what does it consist of? It consists of our samples of our 100 seniors and their GPAs. Now, on the previous slide, we only had 10 samples. So we had 10 proportions of students whose GPAs were higher than 2.0. Those were only 10. There are many possible samples of 100, way more than 10. Okay, so what exactly is the sampling distribution? So what the sampling distribution is I had proportion 1 of the GPAs, then I had proportion 2 of my GPAs, and then I had proportion 3 of my GPAs, and then I had proportion 4, and then I had proportion 5, and then I had proportion 6, and then I had proportion 7, and I had proportion 8, and I had proportion 9, and I had proportion 10. Now, why is it called a sampling distribution? Well, it's a sampling distribution because I took all of my samples, I took all of my sample proportions, and put them in a distribution. All right, so it's not just one proportion, it's all of my sample proportions on one distribution. All right, now notice how this says the sampling model has a mean of 0.750. So that means if I took all of these proportions, so I have 10 p hats, okay, so I have 10 p hats. If I took the mean of all 10 p hats is 0.754. The standard deviation of all of those p hats Okay, so there's our sampling distribution again. Since the mean of the sampling model is 0.754, then p hat is an unbiased estimator of p. So all of those samples are unbiased estimators of P, which is our true population proportion. So it's an unbiased estimator if the true value of P, the proportion of all seniors in Fairfax County with a GPA of 2.0 or higher, is equal to 0.754. Okay? So a statistic can be unbiased and still have high variability. So what does that mean? What does high variability mean? So unbiased means it's a good estimate of the population. Variability means that it's all over the place. So here's a p hat here and here's a p hat here. They're pretty far, they could be pretty far spread apart. If it has high variability, it means they're far apart. Low variability would mean all of my p hats are all about the same value. Okay, and larger samples give a smaller spread. So if I have 50 samples of the 100, that's going to have a lower variability than only 10. Okay, so how can I reduce variability? Larger samples reduce variability, but they won't eliminate bias. So if there is bias, it's not going to eliminate it, it's just going to reduce the variability. If there is a bias, it might show us which direction it's in, because it'd be small variability. It would either be an consistent overestimate or consistent underestimate. Okay, so what is the difference? What exactly is the difference between a sampling distribution and a population distribution? So there are actually 3 different types of distributions when we sample repeatedly and measure a variable of interest. Okay, so we're going to take a look at the next slide for the 3 distributions for whenever we sample repeatedly. So sampling repeatedly is like looking at those 10 proportions of students with a GPA higher than 2.0. So that's repeated sampling. So I had 10 groups of 100 and found the average proportion. All right, so the population distribution gives the values of the variable for all the individuals in the population. So let's say there's 10,000 students in Fairfax County. The population distribution would give every single solitary student's GPA and put that GPA on a distribution. Okay, that's the population distribution. So it's individuals on the distribution. The distribution of a sample data shows the values of the variable for the individuals in the samples. So these two are similar in the sense that the population distribution, if I took all of the students in Fairfax County and put them on a distribution, I would have all of their GPAs. Let's say that I took 100 students and put them on a distribution and found their GPAs. Okay, so if I just look just at one of those samples of 100, that would be the distribution of the sample. The sampling distribution shows the statistics from all the possible samples of the same size from the population. Okay, so let's take a second. Okay, so this would be the distribution of all GPAs of seniors in FCPS. Okay, that is the population distribution. There's no statistics involved. I didn't do anything. I literally just took all the samples, plopped them onto the distribution. Okay, I did no math involved. There was no math. Okay, the distribution of a sample, once again, no math. So this would just be 100 GPAs of seniors. Okay, once again, I didn't do any math. I just took up my 100 GPAs, plopped them down on my graph. How is that different from the sampling distribution? So the sampling distribution is, here's 100 seniors, what's their average GPA? Here's another 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 100 seniors, what's their average GPA? So the sampling distribution has a statistic that creates the distribution. All right, so I took a whole bunch of means and put all of those means into a distribution, that gives us a sample-ling distribution. The other two, there's no math involved. Here, I actually took the sample of 100, found the mean, put that mean in the distribution. Took another sample of 100, found that mean, put that mean in the distribution. And so this distribution is looking at a bunch of statistics. Okay, so hopefully you understand the difference between those three. Okay, so we're going to take a look at the next slide. It illustrates the Okay, so here's just a visual of what that looks like. All right, number one, so we're taking a look at red chips. Okay, this is the population distribution. So this population distribution is basically saying that if they took 200 chips, 100 of the chips would be red and 100 of the chips would be blue. That's the population distribution. There's 200 chips out there, 100 are red, 100 are blue. What does that mean? Our parameter, or our population proportion of red chips, is 0.5. Okay, so it's the parameter of red chips. Okay, so this right here, our population distribution, is all of the data. Now, let's take a look at the distributions of the sample data. Okay, so this is the distribution of each sample of data. So I took 20 chips, and within each of those 20 chips, I found the proportion of red chips. So this is the distribution of one sample. Okay, so the p-hat for that one sample was 0.4. So 40% of the chips were red. Here's my second distribution of one sample. The proportion of red chips in there was 0.55. Here's my distribution of the third sample. The proportion of red chips was 0.65. Okay, so this is population distribution, all the data. Distribution of a sample is one sample looking at just the distribution of one sample. A sampling distribution is all of the p-hats. So I took this p-hat, this 0.4, and stuck it right here. And then I took this p-hat of 0.55 and stuck it, right here. And then I took this p-hat of 0.65 and stuck it in this column. So the sampling distribution, these are all the p-hats. It's like taking all of your sample proportions and putting them in a distribution to create the sampling distribution. So the sampling distribution is made up of statistics. Okay, so it's the distribution of all of the samples. Okay, so let's just take a look at our sampling distributions and take a look at the center. A statistic is used to estimate the parameter. It's an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter being estimated. Okay, so unbiased estimator just means I have a really good sample, so the mean of the sampling distribution is equal to the mean of the parameter. So what is the center? How can I see if the center is biased and unbiased? So in our chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. Okay, so this is all the sample proportion of red chips. So this is a whole bunch of samples of 20. Sample proportion of red chips, so maybe this is like 500 samples of size 20, and here's the proportion of red chips in all of those samples of size 20. The question that we want to answer, how well does the sample proportion estimate the true proportion of red chips, 0.5? Okay, we knew the sample or the population proportion was 0.5. You're not always going to know that. So we're going to have to answer the question, how well does it estimate it? If it does a good job, we can say that the sample proportion estimate is an unbiased estimator for the population. Okay, so if this distribution of our sample proportions is a good estimate of Okay, so how exactly can we answer the question whether or not something is biased or unbiased? All right, because the fact that statistics come from random samples. All right, so remember, random sampling is important. They have definite sampling distribution. So they will have a sampling distribution. They will, either be right skewed, left skewed, or approximately normal. Because they have definite sampling distributions, they allow us to answer the question, how trustworthy is a statistic as an estimate estimator of the parameter. Well, how do we really know if our sampling distributions that we created are good? Are they good or bad? So in order to answer this question, we have to look at the center, the shape, and the spread. Oh, similar. Doesn't that sound like what we talked about in the previous section with socks? Okay, so let's just take a look at this. Notice that the center of the approximate sampling distribution is close to 0.5. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 5. So, but that's you going out and taking every single possible sample of size 20, finding the proportion of red chips, and putting that proportion in this distribution. If we did that, the proportion of red chips of this distribution, so the average number of red chips in all of our samples, would be exactly 0.5. Okay, so that was the center. So the center is going to give us a good estimator of the true population. So when we create our sampling distributions, we want to make sure that we have low variability. What does that mean? That means I don't want data that's spread out all over the place. So in order to get a trustworthy estimate of an unknown population parameter, we start by using a statistic that's an unbiased estimator. Well, what does that mean? This ensures that we won't overestimate or underestimate. So we want an unbiased estimator, remember. Okay, that means that we're not going to overestimate or underestimate. Unbiased estimator means it's going to be similar to the true population. Unfortunately, using an unbiased estimator doesn't guarantee that the value of our statistic will be close to the actual value, actual parameter value. So just because it's unbiased, so unbiased doesn't necessarily mean that it's going to be close to the actual statistic. So let's look at variability. Okay, so variability means when I take a sample, high variability means it's all over the place, low variability means it's close to. Okay, so larger samples obviously have a clear advantage over smaller samples. They're much more likely to produce an estimate that's close to the true value of the parameter. So let's just say that here is 100 samples. We took 100 samples. Let's look at that variability. So that variability is pretty wide. You know, you're starting from 0 going up to 0.52. Okay, so you have sort of proportions that are all over the place. But when I take a sample of 1,000, let's look at those sample proportions. You have a much smaller variability. It takes all of those values and puts them much closer together. So larger samples reduce our variability. Okay. The variability of a statistic is described by the spread of the sampling distribution. So this is, remember, sampling because it's a whole bunch of proportions. Okay. The spread is determined by the size of the random sample. So larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population. So I don't care what the size of the population is. I care more about the size of my sample. One thing that is important is the population has to be 10 times larger than the sample. Now, this isn't just, when I say n is equal to 100, it's not 100 sample proportions, okay? It's size 100 of each of these proportions. So I found the proportion within my sample of 100, put that here. Took another sample of 100, put that proportion here. Took another sample of 100, put that proportion here. Another sample of 100, put that proportion here. Where here, this is 1,000. I took a sample of 1,000, put that proportion here. Took another sample of 1,000, put that proportion here. Took another sample of 1,000, put that proportion here. Another sample of 1,000, put that proportion here. Okay? So these both have equal numbers. So let's say I took okay, let's just say that this consists of 200 samples of size 100. This would be 200 samples of size 1,000. Okay, so both of these have the same number of samples. It's just that when I took a sample, I took 100 here and 1,000 here. So why does 1,000 give us smaller variability? Well, it gives us smaller variability because if I have within that 1,000, if I have a wide range of proportions within that sample of 1,000, if I'm taking the average of 1,000, they're going to average. Okay, so one important and surprising fact is that the variability of a statistic in repeated sampling does not depend on the size of the population. It depends on the size of the sample, not the size of the population. Okay, so it's basically mathematical theory versus the real world. So we're going to be talking about the 10% rule, and we're going to be using this throughout the rest of the course. All right, so the 10% rule is a numerical approximation that we apply in AP statistics. What does the 10% rule tell us? The 10% rule tells us that the population must be at least 10 times larger than the sample. All right, so that if the population is at least 10 times larger than the sample, okay, that helps us to reduce variability. So to understand, if you want to take a look at the underlying mathematical theory as to why that works, take a look at this link right here. But just keep this in mind, that whenever you're taking samples, the population has to be 10 times larger than the sample. So on that previous page, when we had samples of 100, that means that our population should have at least 1,000. If we're taking samples of 1,000, our population has to be at least 10,000. Okay, so that 10% rule, we're going to be applying that. Okay, so let's just take a look at what is the difference between bias and variability. So we can think of the true value of the population parameter as the bullseye on a target. Think of the sample statistic as an arrow being fired at the target. Okay, what is our ideal situation? Here's the ideal. So we have our bullseye, the center right here. This is the true value of the population. Our darts, think of them as the statistics. Okay, if you take a look at this example, both the bias and the variability describe what happens when we take many shots at the target. All right, so this is like your perfect straight shooter here. Okay, let's take a look at this. This one has no bias. Why? Why does it have no bias? Because the mark is right where it should be. The sample, which is our arrows, are right at the population parameter. So there is no bias. There's also low variability. Why is there low variability? Because all of the darts are in exactly the same spot. So no bias means the sample statistic hit the population parameter. Low variability means that they're all in the same spot. I don't have statistics all over. Okay? Both bias and variability describe what happens when we take many shots at the target. So bias means that our aim is off and we consistently miss the bullseye in the same direction. So it's like saying our statistic is off and we consistently miss the population parameter. We hit the same spot every single time, it's just not where we want it to be. It's kind of like getting a gutter ball on the right side every single time you bowl. Okay? So our sample values do not center on the population value. So if you have bias, it means the sample values that we get aren't where they should be at the population. And remember, when we talk about bias, we always want to describe, is it an overestimate or underestimate? So here's an example. This has a high bias. This is it should be right here. Here's where our target should be, but all of our arrows that we shot are far away from where they should be. So it has a high bias, but take a look at the variability. It has a low variability because all of them hit in the same spot. So in this case, I consistently overestimated where my data should be. All right, so high bias, far away, but low variability because I was pretty good at shooting at the same spot. Okay, so let's just take a look at a couple other examples. So when, let's say I miss the mark all over the place, this has low bias and high variability. So high variability, I'm all over the place, but I'm not biased, I'm not consistently over or under in the same direction. Okay, high variability means that repeated shots are widely scattered and repeated samples do not give similar results. So if I was taking a look at the average GPAs and let's say I'd get one that's a 4.3 and one that's a 1.2 and one that's a 3.9 and the other one is a 1.5, okay? The repeated samples are not giving us similar results. They're all over the place. I can also miss the mark in the same area in a wide range. So this one has high variability because my marks are all over the place. It also has high bias. Why does it have high bias? Because they're all in the same direction. This has low bias because they're all over the place. I'm not either always above or always below. Well, here I'm always above, so it does have high bias. So the lesson about center and spread is clear. Given a choice of statistics to estimate the unknown parameter, what you want to do is you want to find one that has no or low bias. You'll almost never eliminate bias. You're probably going to over or underestimate a little bit. And you also want to find the minimum variability. That means basically we want all of our shots to be in the same area. So how can we reduce variability? Okay, so what exactly does this mean? What is accuracy? Accuracy means that our estimate's in the right spot. Precision means that our estimate has low variability, but it doesn't mean it's in the right spot. So if I'm a precise shooter, I shoot in the same spot every time, but it just might not be right. Accuracy means that I'm shooting in the correct spot every single time. So just be really careful with your wording. Okay, here's an incorrect statement. Our estimate will be more accurate if we increase the sample size. Well, our estimate isn't more accurate if we increase the sample size. Accuracy is like saying that our estimate's in the right spot. What does increasing the sample size do? Okay, increasing the sample size is not going to put our estimate in the correct spot. However, it's going to make it more precise because remember, we said increasing the sample size gives us a lower variability. So if we have lower variability, then we're going to be more precise. Just doesn't necessarily mean it's going to be more accurate. The correct statement would be our estimate will be more precise in the correct or in the same spot if we increase the sample size. Okay, so let's just take a look at this example. A sampling distribution can take on many shapes. Okay, they don't have to all look approximately normal. The same statistic can have sampling distributions with different shapes depending upon the population distribution, the sample size. So if we take a bigger sample size, we're going to have much lower variability than if we take a really small sample size, we're probably going to have high variability, and the shape of my distribution can look very different. Be sure to consider the shape of the sampling distribution before doing inference, and we'll discuss later on what the sampling distribution should look like before we do inference. All right, so let's just take a look at this example. Here are 5 sampling distributions for 4 different statistics used to estimate the number of German tanks in World War II. Okay, so those are just 4 different methods that people used in order to estimate the number of German tanks in World War II. This blue line right here represents the true number of tanks, the true number of German tanks in World War II. Okay, so let's just take a minute and take a look at the graphs of 5 sampling distributions. So the graph below shows the approximate sampling distribution for different statistics when taking 250 samples of size 4 from a population of 342 tanks. The line represents the true mean of the population. All right, so let's just take a minute and understand what this 250 samples of size 4 means. So that means I took a sample of size 4, found the mean, put it on my graph. Took another sample of size 4, found the mean, put the mean on my graph. Found another sample of size 4, found the mean, put that mean on my graph. I did that 250 times. So each of these dots represents a mean, okay, from the sample of size 4. Since they each represent a mean, each of those little dots is a statistic. Okay, so it's the statistic of the sampling distribution. All right, so just understanding what a sampling distribution and statistic within that sampling distribution, what that represents. So let's take a minute and answer questions A, B, and C. So A, which of these statistics appears to be biased? Explain. Of the unbiased estimators, which is best, explain. Explain why a biased estimator might be preferred over an unbiased estimator. Now just remember, in statistics, we're always pretending that we are giving this information to somebody that knows nothing about statistics, and they should hopefully be able to read and understand and interpret what you've told them. So make sure you have a thorough explanation. Okay, so we knew from the previous slide that the mean number of tanks was 342. So that blue line represents that mean of 342. So we were first talking about bias estimators. So let's look at graph B and graph E. Graph B and graph B and E, appear to be biased because they're consistently too low. So remember, what's a biased estimator? A biased estimator means they are consistently estimating the population mean or proportion in one direction. They're either consistently overestimating the population or consistently underestimating the population. So if you take a look at B, it's biased because all of those are much smaller than the true mean. So this is underestimating the population. If we take a look at E, okay, there's a few that are above, but consistently most of them are underestimating the mean number of tanks. So they're all below the 342. Okay, that is, the centers of their sampling distributions appear to be below the correct value of 342. So all these means were less than 342 when they should have been right around 342. All right, so let's take a minute and look at the unbiased estimators. So there were 3 unbiased estimators, so A, C, and D. All right, which one is the best? So A is actually the best because it has the least variability. So I'm only going from about 100 tanks to about 400, where if we take a look at the other ones, we're going from, maybe 50 to 600 or 50 to 650. So C and D had a much more variability. They were much more spread out than A. A had the least amount of variability. All right, so taking a look at our 2 biased estimators, even though B is a biased estimator, biased because it's consistently too low, it often produces estimates, if we take a look right here, very close to the truth. C, although C is unbiased, if we take a look at C, it's quite variable. So it's not biased, but it's not variable, and it's not really close to the true value as often as it should be. So for example, in 120 of the 250 simple random samples, B produced an estimate within 5 of the true value. So right here, 120 of those 250 samples were only 5 below the mean of 342 tanks. However, C was close in only 79 of the 250 samples. Okay, so just because, when we're looking at graph C, all right, now it has a lot of variability, but it's not biased. So biased, even if it misses the true mark, okay, even if a lot of them miss the true mark, it doesn't mean it's biased. Bias specifically means that it's consistently, there's a lot too low or a lot too high. Okay, so in this case, there's a lot too low, a lot too low. And these two, they're kind of just all over the place. So they do have a lot of variability. Okay, but in this one, this biased estimator is actually better because even though we were consistently too low, we were pretty consistently close to the true population of 342. Okay, so unbiased estimators are not going to be perfect. So these are definitely not perfect. They have a ton of variability. Remember, unbiased just means it won't be consistently too high or too low. So unbiased doesn't necessarily mean it's going to be perfect. The center of your sampling distribution will be in the right spot. So it's telling us that the center is in the right spot. So here's my sampling distribution. The center and the mean is right on 342. So that's telling us that the mean is correct, but it doesn't really mean it's a Okay, so when we assume that we have an unbiased estimator of the population, we also assume that the sampling process has no bias. All right, so that means that when we took the simple random sample of the 4 tanks and found that mean, we assume that getting the SRS of our 4 tanks was done without bias. So what does that mean? We assume that the sample we used was a simple random sample, so that is a very important condition of our sampling distribution, is that the sample that we used was a simple random sample and not a convenient sample or a voluntary response sample. Those are not simple random samples. For example, even though that X bar is an unbiased estimator of mu, or the population, the sample is an unbiased estimator of the population, asking people in person how much they weigh will probably consistently produce estimates that are too small. So in this case, it will be an unbiased estimator because it's going to be consistently too low. All right, so what do we need to know about the AP exam and sample-Ling distributions? Be careful with the distinction between the distribution of a sample and a sample-Ling distribution. So remember, the distribution of a sample Okay, so in this section you learned how to distinguish between a parameter and a statistic. Use the sample-Ling distribution of a statistic, so all your means or p-hats, to evaluate a claim about a parameter. Distinguish among the distribution of a population, a sample, and a sample-Ling distribution. Determine whether or not a statistic is an unbiased estimator of the population, and describe the relationship between sample size and the variability of a statistic. So in the next 2 sections, we're going to specifically take a look at the sample-Ling distribution of a mean and the sample-Ling distribution of a proportion.